Welcome to The Explainer. Today, we're going to talk about an invisible force that's all around us. It's what cools your coffee, it's what drives our weather, and it's what makes high-performance engines even possible. We're diving into the fundamentals of convection. And it all really starts with a question you've probably never thought to ask.
I mean, seriously, why? We all do it. It's just second nature. But the answer unlocks this whole incredible world of fluid dynamics and heat transfer. And by the end of this, you'll know exactly what's happening in that soup bowl.
So at its very heart, convection is just heat being moved around by a fluid that's in motion. That's it. And the fluid could be anything: air, water, even the oil in your car. If it's moving and it's carrying thermal energy from one spot to another, boom, that's convection.
Now, to really get a grip on convection, it helps to see it next to its cousin, conduction. Conduction is when heat just kind of creeps through something that's still. Think of a metal pan on a stove. The heat just passes from one molecule to the next all the way up the handle. But convection, it absolutely requires motion. The fluid itself physically moves in bulk, carrying that heat along for the ride. And that right there is why it's so much more powerful.
Okay, so convection itself actually comes in two main flavors. And our soup example, it's perfect for this. If you just let your soup sit there, you're looking at natural convection. The soup heats the air right above it, that air gets lighter and rises, and cooler, denser air sinks to take its place. It's a natural cycle. But the moment you blow on it, you've just created forced convection. You're using an outside force, your breath, to make that air move, and as we all know, that cools things down way, way faster.
So, we've established that motion is the key ingredient. But to really, truly understand what's happening, we have to zoom in. I mean, way in. Right down to that invisible layer where the fluid, the air, is actually touching the surface of the soup. This is where the real story unfolds. And the very first thing we see when we zoom in is this absolute, non-negotiable golden rule of all fluid flow. It's called the no-slip condition, and it basically says that any layer of fluid touching a solid surface stops. It comes to a complete halt. It sticks to it. It sounds almost too simple, but this one little fact is the reason for everything that comes next. So, how does this one stuck layer affect everything else? Well, picture it. You've got this stream of air moving along, right? The instant it hits the surface, that bottommost layer just stops dead. Now, because of the fluid's own internal friction, what we call viscosity, that stopped layer acts like a little brake, and it starts dragging on the layer of air just above it, slowing it down. And that layer then slows down the one above it. You get this domino effect, this cascade, that creates a whole region of slowing down fluid. This zone of influence is what we call the velocity boundary layer. And here's where it gets really cool. The exact same thing happens with temperature. So if your cold air is flowing over that hot soup, that first layer of air that's stuck to the surface, it heats up to match the soup's temperature. And then it starts warming up the layer of air above it, which warms the layer above that. You get another one of these gradients, but this time for temperature. We call this, you guessed it, the thermal boundary layer. So you've got these two invisible layers, one for speed and one for heat, both born from that contact with the surface.
But wait, there's more. The story doesn't just stop with these layers. Because the flow inside those layers, well, it can have two very, very different personalities. It can be either super well-behaved or completely wild.
On one side, you've got laminar flow. Think of pouring honey. It's smooth, it's polite, the layers just slide past each other nice and cleanly. But on the other side, you have turbulent flow. This is a raging river. It's chaotic, it's messy, it's full of these swirling eddies. And here's the kicker. That constant, chaotic mixing makes turbulent flow an absolute beast at transferring heat. All those little eddies are like tiny hands constantly grabbing heat from the surface and tossing it out into the main flow.
So, what is it that decides whether the flow is going to be that nice, smooth honey or the chaotic, raging river? Well, it all comes down to a constant battle between two forces that are always competing inside the fluid. And the referee of that battle is one single, incredibly powerful number, the Reynolds number. The easiest way to think about it is as a ratio.
In one corner, you have the fluid's inertia. That's its tendency to just keep going, to be chaotic. In the other corner, you have the fluid's viscosity. That's its internal stickiness, the thing that resists change and tries to keep things orderly. If the Reynolds number gets high enough, inertia wins, and you get chaos, turbulence. If it's low, viscosity wins, and the flow stays smooth and laminar.
So is there like a magic number? A specific tipping point? Well, for a simple case, like air flowing over a flat plate, yeah, there is. The number that engineers generally agree on is right around 500,000. You stay below that number, and your flow is probably nice and laminar. You go above it, and things start to get turbulent. It really is like a speed limit for keeping things orderly.
Okay, so now we get to the really, really cool stuff. Because once we understand all these pieces, we can start to see how engineers have basically developed a kind of secret code, a set of tools that lets them predict and control all of this with incredible precision.
The first piece of that code is the Prandtl number. This one's all about the fluid itself. It basically asks a simple question. In this particular fluid, which spreads faster and easier, motion or heat? It's really just comparing the thickness of that velocity boundary layer to the thermal one. For something like air, the number's about 1, so they're roughly the same size. But for, say, thick motor oil, the Prandtl number is huge, which tells us that momentum spreads way easier than heat does.
And the next tool in the box is the Nusselt number. You can think of this as the final report card for your convection. It gives you one clean number that tells you exactly how much better your moving fluid is at transferring heat compared to if it was just standing still. So if your Nusselt number is 1, that's pure conduction. That's a failing grade. But if your Nusselt number is, say, 100, whoa! Now you are moving some serious heat.
This all leads up to one of the most beautiful and powerful ideas in all of engineering, often called the Chilton-Colburn analogy. And this is the real secret sauce. It reveals that the physical laws that cause friction or drag on a surface are fundamentally the same laws that control heat transfer. Let that sink in for a second. That's a complete game changer. It means that if you can measure the drag on a radiator, you can predict exactly how well it's cooling. You measure one, you know the other, it's an incredible connection.
And this secret code, understanding Reynolds, Prandtl, Nusselt, and that deep link between friction and heat, it's not just theory. It's literally how we build the modern world. It's in the design of the CPU cooler that's keeping your computer from melting right now. It's in every jet engine, every power plant. It helps us build faster cars, predict hurricanes, and yep, it even explains the best way to cool down that slice of pizza before you take a bite. So the next time you feel a cool breeze on your face or you blow on your hot soup, you'll know there's this incredibly elegant dance of physics happening right there. It really makes you wonder, doesn't it? What other invisible fundamental forces are out there silently shaping every single moment of our world?